Hi, chemists! Today we're going to be continuing to think about factors that affect the rate of a chemical reaction. This is the second sequence of lessons about factors that affect the rate of a chemical reaction. Today we are going to be talking about temperature and surface area. So our learning goals are to define temperature and surface area in terms of particles in chemistry, and then to explain how changes in temperature and surface area affect the kinetics of a chemical reaction. We will use simulations as well as looking at a real-life example to think about how these two properties and variables can affect how we think about collision theory in chemical reactions. Let's get to it. A quick reminder. For a reaction to occur according to collision theory, two things must happen. Reactant particles must collide with enough energy to break any bonds holding the particles together, and reactant particles must collide in the correct orientation for new bonds to be formed. So the more collisions that occur, the higher the probability that both of these needs will be met. The term temperature, very simply, just means a measure of the average kinetic energy of a sample of matter. If we are thinking about wanting to be able to describe a substance with a high temperature, right, as humans, we would think of something that feels hot to the touch. As chemists, what we would think about seeing if we could put on our zoom-in particle goggles is that in a higher temperature substance, the particles on average are moving physically faster than the particles would be in a lower temperature substance. So in a higher temperature substance, the particles are moving faster, their average kinetic energy is higher. In a lower temperature substance, the average particle is moving slower. Notice as we increase the temperature on this sample, the biggest change that we see to the actual particles is simply that they start moving faster. As we decrease the temperature, as we cool down the substance, the biggest change that we see is that the particles start moving more slowly. Let's look at a real-life example. You may have used Alka-Seltzer in the past. Alka-Seltzer tablets are solids that contain several different ingredients, including solid citric acid and solid sodium bicarbonate, which are mixed together in these tablets. When these substances dissolve in water, they then react with each other, the citric acid and the sodium bicarbonate, producing the carbon dioxide bubbles that we see when Alka-Seltzer tablets start fizzing. By timing how long it takes for the tablet to stop fizzing, we can determine how quickly reactions are happening. So we are going to do a mini controlled experiment. I have two equal amounts of water, and I have two identical Alka-Seltzer tablets that I'm going to drop into the water. One of the water temperatures is cold. The other water temperature is hot. I use tap water from my sink, so I don't have exact degrees, but the water on the left is cold water, the water on the right is hot water from the tap. I dropped both of the tablets in at the same time, and we can see evidence that a reaction is occurring because we can see the production of a gas. We can see the bubbles. And it seems as though, if I'm observing here, it seems as though the hot water is a little bit foggier, though it could just be the way that the tablet has moved around. Let's see if one of the jars seems to stop bubbling first. So I'm noticing that the hot water jar has already started to get a little bit clearer, and the bubbles have pretty much stopped. Meanwhile, the cold water jar, the tablet is still visible and reacting. The tablet is completely gone in the done reacting jar. It has completely dissolved, and the sodium bicarbonate and citric acid have completely reacted. The cold water is still bubbling a little bit, and it seems to just be stopping. So it seems as though the hot water has a faster rate of reaction than the cold water when we place the Alka-Seltzer tablets in the jars. So it seems as though increasing temperature appears to increase the rate of a chemical reaction. Let's think about why this might be in terms of particles. So if we increase the temperature, we are increasing the rate of the reaction because if particles are moving faster, that means more collisions can occur in a given amount of time. If more collisions can occur in a given amount of time, we will have more of a likelihood of successful collisions to start a reaction. Now let's define surface area in the context of chemistry. You may have heard of the definition of surface area in math class as the measurement of the perimeter or the total area around the surface of a three-dimensional object. Now, the way to think about that in chemistry is thinking of surface area as a measurement of the outer layer of a three-dimensional substance. If you're thinking about a present wrapped up in wrapping paper, the amount of wrapping paper that you would have to use represents the surface area. It's the outermost layer of that substance. And so if we think about an actual physical substance made up of particles in a solid, surface area usually is applying to solids. The larger the surface area of a substance, the more particles there are exposed to the surroundings. The more particles there are up at the surface exposed to the surroundings. The smaller the surface area of a substance, the fewer particles there are exposed to the surroundings. We're going to look at a real-life example right now. So I'm going to break each of these tablets up into different numbers of pieces. The first tablet is just broken, or not broken at all. The second tablet is in half, third is in quarters, and the fourth is split into eighths. Now, the tablet that I did not split at all actually has less surface area than the tablet that I crushed into eighths. And if I were to continue crushing the tablet, it would gain more and more surface area because every individual piece has its own set of surfaces, and I'm maximizing the surfaces by breaking it apart. So I put each of these tablets into a jar of water with the same amount of water at the same temperature, and I am just watching to see which one finishes reacting first, which one has a greater rate of reaction. And so I put all of the pieces of each tablet into each jar so that the only difference between each of the tablets is whether or not they have been broken into pieces and therefore their surface area. Remember, the most surface area is on the far right, the most broken up, the most crushed tablet, and that's the tablet that finished reacting first. It's a little hard to see in this video, but if you zoom in, and you can even try this at home, that tablet stopped making new bubbles first, then 3, then 2, and then finally the first jar, which contained our whole tablet. Took the longest amount of time to finish the reaction, and I could tell the reaction was done when I stopped seeing new bubbles being formed that represented the carbon dioxide in the reaction being formed. So this gives me some idea of the relationship between surface area and rate of reaction. What do you think that relationship would be? Right, we noticed that number 4 finished reacting first, then number 3, then number 2, then number 1, right? So if we think about what's happening in terms of particles, it does make sense. An increased surface area allows particles to collide more often. Larger surface area leads to more collisions and therefore a faster rate of reactions because more particles are able to collide with each other. Let's recap what we've learned in the last 2 videos. To increase a reaction rate, we're going to think about what we would need to do to concentration if we have a liquid or a solution, to pressure if we have a gas, to temperature, and to surface area if we have a solid. So if we have a solution or a liquid, a higher concentration of that solution will lead to more collisions, which will lead to a faster rate of reaction. Again, tying everything back to collisions. Higher concentration, more collisions, faster reaction. If we have a gas, a higher pressure of a gas will also lead to more collisions. So if we have a gaseous reactant and the pressure is increased, that will lead to more collisions, which will lead to a faster reaction rate. If we have a higher temperature, if we increase the temperature in any sort of reaction, we will lead to more collisions, which will lead to a faster reaction rate. And if we increase the surface area of a solid, usually by grinding it into a powder or into smaller pieces, that will also allow more particles to collide with each other and lead to a faster reaction rate. Nice job today. Before we go, let's check back in on our learning goals. Make sure you can define both temperature and surface area the way that a chemist would, in the way that is the most relevant to particles and collision theory. And then think about Can you explain how changes in temperature and surface area would likely affect the kinetics of a chemical reaction in terms of collision theory? Have a great day.